All right, chapter 15, think and solve. There are two problems from this, and both of them are using this formula that in my version of the textbook is misprinted. And so I think for later printings, just like in the previous section in the plug and chug, I think this got corrected, but I'm not 100% sure. So if you're looking at an older textbook or they didn't correct it, it should be delta L equals alpha L delta T, or L sub 0 delta T, and or delta L divided by L equals alpha delta T. So we can multiply by the original length on the right or divide by the original length on the left. Either way is fine. So just so what these mean, delta L is the change in length. Alpha is the expansion coefficient, that is material specific. L, or L sub 0, is the original length before the heating happened, and delta T is the change in temperature. So some of the language here, they use the term similarly heated, and we've got to be careful about that, because heat is the amount of energy you put into a system, and he's not claiming that you're putting the same amount of energy in, because it's of the same material. I think I can easily make the case that a 100-meter bar, it's not necessarily, but a 100-meter bar probably is going to have more material than a 1-meter bar, or more mass, and therefore putting the same amount of heat in would cause a different change in temperature, which causes a different change in length. However, what he's going for here is that the change in temperature is the same. So similarly heated is sort of vague terminology there. I think he's sort of taking us out of the physics language, putting us into everyday language. But the change in temperature we have to assume is the same. So we're looking at basically a ratio here. We don't know material, we don't know the actual change in temperature, we do know alpha, but we can solve for alpha delta T, because that's going to be the change in length over the original length. One thing you got to be careful on is units here, because in the first bar is 0.6 centimeters. Change in length is 0.6 centimeters from the original length of 1 meter, and so that would be 0.006 meters. So we're looking at a ratio of 0.006 meters over 1 meter would be equal to alpha delta T, which there would also be equal to delta L over 100 meters for the other bar, and you do the math and you end up with delta L for the larger bar is 0.6 meters, so the new length would be the original 100 plus delta L, which is 0.6. So that's 39. 40, we have 1.3 kilometer main span of steel, and show increase the temperature the bridge would be nearly 0.3 meters longer. Again, the language here is sort of makes it sound like the bridge is actually longer. Usually the bridge does not lengthen. They have gaps there to account for that. So the bridge itself, if you count the bridge as being from one shore to the other shore, that's not really changing significantly here. But this main span of steel would change, and that's what we're looking for here. It is steel, and the expansion coefficient is listed in the italicized, the flavor text up above. Alpha is equal to 11 times 10 to the negative 6 per degree Celsius. And we're increasing temperature of 20 degrees Celsius, and so the change of length is equal to alpha, the 11 times 10 to the negative 6th, times the original length, which is 1.3 kilometers or 1,300 meters, times the change of temperature, which is 20 degrees Celsius, and multiply it out, and you should get 0.3 meters, which would be the change in length. And I think that's it for Think and Solve.